dude. Right there.
Ether, don't you just have to click one button?
It wasn't even on. GPS?
Okay,
Yeah, come on.
so here's what we've got so far.
Papa.
So the first two equations that are up there, that's actually what's on your equation sheet. Okay? Those are the first two. This other one, this is the 1/2 e plus v naught time. That isn't on your equation sheet, but sometimes that's handy to have. And again, all you're taking is just like the average of two velocities and you're multiplying it by time. Okay? That's all there is to it. So there isn't a lot to memorize. So one option is I take the average of two. There you go. So let's say that we want to do like a real world application of this. So let's say that I've got yonder fan cart, okay? And we can turn this on. It's going to get up to speed. And then I'm going to let go of it. And oddly enough, it begins to accelerate. Okay? So I'm going to turn this on. I'm going to let it go. So what are some things that we could measure as that cart speeds up? Keaton, tell me one thing that I can measure.
I guess the time it takes to get to a certain point.
Okay, I can measure time. All right? That's going to be some value. I happen to have a stopwatch just for such an occasion. I got a stopwatch. I can measure time. Okay? What else can I measure?
Distance.
I can measure distance. Ah, I can measure how far it's going to go. Okay? Now, if I'm clever, what do you think I'm going to let my initial velocity be?
Zero.
Zero. Okay? Because then I don't have to worry about that in the equation. So I'm going to try and find my acceleration. That's my ultimate unknown, right? So I can measure time. I can measure displacement. I can know that my initial velocity is going to be zero. Okay? So let's go with this idea. So what I'm going to do is I'm going to give that a little twist over here so the studio audience can see what's going to happen. So Louis, I'm going to trust you to do the timing. You ready?
Hang on, I gotta figure out the buttons. Got it.
Got it? Okay, so I'm going to get this up to speed, right? Before I'm going to let it get all the way up to speed before I let go of it. Okay? So we're just going to let it travel 1 meter exactly.
Do you want me to start when you let go?
Yeah, so I'm going to go 3, 2, 1, go. All right, you ready? 3, 2, 1, go. Stop.
4.9.
4.9.
4.9?
4.9.
On the dot.
Exactly?
Yep, exactly.
Cool.
Just messed up.
So we got 4.90 seconds. It traveled exactly 1 meter. Now I'm going to try and find this acceleration. So start with this, okay? What would the position time graph look like for that motion?
Like half of the parabola? Or,
Something like this?
yeah,
Why?
it's increasing velocity.
We're speeding up, right? Slope of the position time graph gives you velocity. It was speeding up, parabolic curve, right? Now, what about the velocity time graph?
Straight sloping line.
Boring, but correct. Why?
Because
It's
velocity is
increasing.
increasing at a constant rate.
Because we assumed that F equals ma. We didn't change the mass. The fan was already up to maximum speed when we started. So if the force is the same, the mass is the same, acceleration is the same, right? Now, obviously, if we let that cart roll far enough, it would eventually that velocity time graph would plateau out, okay? It isn't like I'm going to let that thing go for miles and eventually it would break like the sound barrier, which would be cool, okay? But eventually, it's just going to reach a point of constant velocity. But over this, we're going to assume that it's going to speed up. Now, if I were to find that area, what would be the numeric value of that area?
Oh, displacement.
How far did it go?
Yeah.
1 meter.
Yeah.
I don't know the numbers, but I know if I were to find that area, that's gonna have an area of 1 meter, okay? Do I know the slope of the line? Nope, because that's my acceleration. I don't know that. Do you know my final velocity?
No.
To find my final velocity, could I do this? To find my final velocity, could I take 1 meter, what was that time, 4.9?
Yeah.
Could I take 1 meter and divide that by 4.9 seconds?
No.
You shake your head no. Why?
Because that's only when it's a constant velocity.
Yes, is this a constant velocity?
No.
For the love of physics, no, it's not. Don't do this. Okay? Don't do that.
But I don't know.
But, can I find my acceleration?
Yes.
Yes.
How?
By seeing.
Slope.
But I don't know enough information to find the slope because I don't know what the final velocity is.
You can find the final velocity.
No, I can't.
You know the time and the area. So you could use that to find the height.
Easier way. Find the acceleration.
Plug it in that formula.
Well, that narrows it down.
The I don't know the name of it.
Oh, you could do the first. Yeah, the first one, but you need to rework it so it's actually looking for acceleration.
Don't use the first one.
The second one.
Third one.
How about x equals 1/2 at squared plus v naught time?
Yeah.
What's your initial velocity?
0.
You don't have to worry about that part of it, right? That all goes away. Do you know how far it went?
Yep.
Yep. Do you know the time?
Yep.
Yep. Can you find the acceleration?
Yeah.
So then you can go 2x over t squared gets me my, so somebody do this. Somebody take 2 times 1 meter. And then what was the time? 4.9? Now, here's what you're gonna do wrong. And you say, Mr. Burkamp, we won't do that, you lie.
24. 2.4.
You're gonna forget the square root this time, okay? That's what you're gonna do wrong. You're gonna take 2, you're gonna divide it by 4.9, you're gonna call it good, okay? Train wreck. You have to square root of that time. So what do you get as the acceleration? It's gonna be a pretty small number.
0.08.
What'd you get?
0.08.
Exactly?
Or 0.083282. Yeah.
We could have 3 significant digits. 0.0832,
3.
3.
Yeah. If you want to count.
Now, if you compare that to the acceleration due to gravity, okay, that's 9.8 meters per second squared. So this is not a very big acceleration at all, okay? But remember, acceleration is not how fast you go. It's the rate at which your velocity changes. So all this says is that for every second that goes by, my velocity changes 0.0833, okay? That's what acceleration is. It's not how fast you're going. Now, if I go back up to my graph, now I do know, now I do know the slope. Now I do know that slope is 0.0833 meters per second squared. Now, pop, can I find the final velocity?
Yes.
Why?
Because you have this slope, so you can. Yeah.
Plug it in.
So, yeah.
Good job.
Yeah, because you can,
I
yeah.
don't know how to word it. Yeah, you can.
What's scary is that I know exactly what you're talking about.
Yeah.
So if you go, if let me translate, yeah, you can, yeah, okay? What that translates into is that, Mr. Burkamp, we know that V equals V naught plus AT. It's a slope-intercept formula. V naught is
0.
my y-intercept, which is going to be
0.
0, because we were clever and we let it start at 0. Okay? I know my acceleration is 0.0833 meters per second squared, and the time was 4.9.
Yeah.
4.9 seconds. So my seconds cancel, I cancel out one of my seconds, I get meters per second, which is velocity winner winner chicken dinner. What do you get? So somebody take 0.0833 times 4.9.
0.40817.
What'd you get?
0.408.
0.408 meters per second. So this is a situation where you can take a little bit of data and figure out a lot of information from it. If I ask you to draw like vector diagrams showing the motion, which is going to happen on this assignment, all I would expect you to do is say, okay, here's like V1. So if you draw V1, when you draw V2, one of two things is going to happen. Either your velocity vectors are getting bigger or your velocity vectors are getting smaller. What do you got? What's it going to do? Connor, what's it going to do?
Get bigger.
Yeah. So then you're going to draw V2 something like this. You don't have to know the numbers, it's just showing that it's getting bigger. So now, since I'm speeding up, which direction is my acceleration vector going to point? Same direction, opposite
Same
direction. Same direction.
Crazy.
Because literally, every problem that I gave you, I have two choices. Do I make it speed up? Do I make it slow down? Does it go in the same direction? Does it go in the opposite direction? Okay? That's a two-trick pony. When I write these questions, that's the decision that I have to make. Okay. Now, let's say that we're going to take the carrot car, and we're going to start it at rest, and we're going to make it accelerate at 4 meters per second squared. Okay? And what I want to know is how fast it's going at the end of 1 second, 2 seconds, 4 seconds. So I want to know how fast it's going. And then I also want to know how far it's gone. So imagine, here's the carrot car. It's going to start at rest. It's going to accelerate at 4 meters per second squared, which is a fairly decent acceleration for a car. I mean, that isn't bam, you're not flooring it. Flooring it gets you an acceleration probably around 8 or 9 meters per second squared. So it's a fairly decent acceleration, but it isn't like, oh, kind of thing, okay? All right? So I want to figure out how fast, how far. I want to draw a position time graph, and then I want to draw a velocity time graph. So let's tackle this. So if you like doing the variables, like, let me know what I've got. So if you want to start a problem like this and do the V naught, dat, that's cool. Because what's your initial velocity going to be?
0.
0. Car's going to start at rest. That's 0. My final velocity, I don't know that. I don't know my distance, but I know my acceleration is 4 meters per second squared. I also know my times, which is 1, 2, 3, and 4. So I know my times, 1, 2, 3, and 4 seconds. I know my acceleration is 4 meters per second squared. I know I don't know my final velocity, and I don't know my distance. Okay? So start with the position time graph. Position time graph is going to be linear or curved? Louis?
Position time graph?
Yeah.
It's going to be curved
Why?
because acceleration is constant.
I'm going to be speeding up. I know my position time graph is not going to be a straight line. What about my velocity time graph? Vitor?
It's just gonna be a straight slope.
Like this?
Yeah,
And what's the value of that slope?
4 meters per second squared. Yeah.
Okay? Now, there's a couple of ways you can approach this. Okay? Let's just think through the big picture. You're starting at 0. And you're going to accelerate at 4 meters per second squared. So at the end of 1 second, how fast are you going to be going?
4 meters per second.
4 meters per second. That's what the number means, right? So at the end of 1 second, you're going to be going 4 meters per second. At the end of 2 seconds, you're going to be going 8. At the end of 3, you're going to be
12.
At the end of 4, you're going to be
16.
16. So if you like just, let me just think this through. Yeah, I'm going to go from 4 to 8 to 12 to 16. Oh, my final velocity is going to be 16 meters per second. Okay? So that's one option. Cool. Now you go, Mr. Burkamp, that's mental math, and man, I don't trust myself. Let's do an equation. Fine, let's do an equation. So we know V equals V naught plus AT. True?
True.
It's a linear function. That's all it is. It's a linear function. It's physics. It's a linear function. Sorry about that.
Plus.
Of y equals mx. That's all it is. Okay? We don't have to worry about the y-intercept because the car's started at rest. It's a slope. So we're going to have 0 plus my acceleration of 4 meters per second squared. And then basically, I'm going to plug in times. I'm going to plug in 1 second, 2 seconds, 3 seconds, 4 seconds. So this velocity is going to go from 1, at the end of 1 second, I'm going to be going 4 meters per second. Then 8, then 12, and then 16. Okay? Now here's what's important. My velocity time graph is going to be a linear function because it's a linear function. Acceleration changes as a linear function of time. Okay? See, my velocity changes as a linear function of time. So this is what that means. Every second that goes by, this is how much my velocity changes. So this is why my velocity time graph is linear. Because that's my acceleration. That's how the rate at which my velocity is changing. Okay? Cool with that?
Cool.
Now, I want to figure out how far it's gone at the end of 1 second. Could I do this? Could I go, at the end of 1 second, I'm going 4 meters per second. I'm going to take 1 times 4, and I went 4 meters. Pop, you're saying no. Vitor, you're saying yes. So you're saying, Vitor, I could take 1 second times 4 meters per second and go, I went 4 meters.
Well, no, because it's not
You said
constant.
yes?
Well, it's not constant.
Oh, why?
Well, because it's not constant. Like velocity is not constant.
Why is it not constant?
'Cause it's
Constant's not
accelerating.
constant. Okay,
It's accelerating.
it's accelerating. Oh, there's my answer. That's what I want. Okay, that's what I want. What's the only time that it's going 4 meters per second?
At the end
At
of
the
1
1
second.
At the end of 1 second. It's going 2 meters per second. It's going pi meters per second. It's going 0.8 meters per second. Okay? It's going across this continuum. Only at the end of 1 second is it going 4 meters per second. Okay? Now, there's a couple of different ways you can find the displacement. I'm going to give you options. Okay? It'll sound like an infomercial. But wait, there's one. Could I find this area? Go, Mr. Burkamp, I love finding areas of triangles. That's my thing. Okay? That's my thing. Do you have enough information to find the area of that triangle at the end of 1 second?
Yes.
Becca,
Yeah.
do you know the base?
Yeah.
Do you know the height?
Yeah.
What's my height?
4 meters per second.
How do you find the area of a triangle?
Base times height divided by 2.
That's right. So if you go, Mr. Burkamp, oh, this is a triangle. I know how to do this. Don't try and trick me. So this is going to be 1/2 times 1 second times 4 meters per second. Oddly enough, I get 2 meters. It's cool. Good area. Okay? Right. Now you go, Mr. Burkamp, I like equations. Okay, cool. You could do distance equals 1/2 v plus v naught times time, which is basically the exact same thing that you're doing up there. You're finding the area of a triangle. It's the average. What's my average velocity? Oh, my average velocity is 2 meters per second. That's kind of cool. It's my average of 0 and 4. Wow. Here's my base, 1 second. Godly enough, I'm still going to get 2 meters. 2 meters. God, Mr. Burkamp, I don't like this method. Personally, I don't like this method. I don't like either one of those methods. And I'll tell you why I don't like either one of those methods. Because if my final velocity of 4 meters per second is wrong, God forbid, but if that's wrong, all of my answers are wrong in terms of how far I went. So you generally want to try and avoid using derived values as long as you can. You want to try and work off of known values as long as possible. Now, you are going to reach a point where you have to take a leap of faith, where you have to use derived values. But you want to put that off as long as you possibly can. So what I want to look at is the distance equals 1/2 AT squared plus V naught time. Now, I like this because it's going to be more of a hidden truth, okay? First off, my initial velocity is 0. I don't have to worry about that, okay? The other thing that I can see is that because it's time squared, I'm going to have time squared. So what's that graph going to look like? Parabolic curve. What did we say my position time graph is going to look like? Parabolic curve, okay? The other advantage of this is that it isn't dependent upon my final velocity, okay? That's why I like this particular equation better. Because if my final velocity is wrong, my displacement's wrong. This goes off my known values. Now, basically, I'm going to have x equals 1/2 times 4 meters per second squared times 1 second squared, which oddly enough gets me 2 meters. Now, here's what's important. I can't have my area of a triangle give me one answer. I can't have distance equals 1/2 E plus V naught times time give me another answer. And distance equals 1/2 AT squared give me another answer, okay? I was like, which one's right? I don't know, I got 3 different answers, right? They all are going to produce the same answer, okay? It's the area, it's an average velocity times time, it's a quadratic function, okay? But here's what's important, and here's the contrast that I want you to see. When you look at, we'll do a little compare and contrast. When you look at V equaling V naught plus AT versus distance equaling 1/2 AT squared, notice that this is just acceleration times time. That makes that a linear function, okay? Because your acceleration is changing as a linear function of time, okay? This is t squared. As soon as you multiply it by t squared, now what does it become?
Parabolic.
Now it becomes a parabolic or a quadratic function. So this means it's going to be a quadratic. So anytime it's just acceleration times time, or whatever it is, it's some constant times time, and there's nothing squared, that's a linear function. As soon as you see something squared, then it becomes a quadratic function. Okay? So at the end of 1 second, I went 2 meters. So if I come back up, way up here to this graph, okay? All right? So at the end of 1 second, I had gone 2 meters. So at the end of 1 second, I had gone 2 meters. Now at the end of 2 seconds, stop. At the end of 2 seconds, I'm going to have 1/2 times 4 meters per second squared times 2 seconds squared. So that gets me 4 times 4 is 16. Half of that gets me 8 meters. Okay? So now I come up here, I'm at 8 meters. Now, don't look at this and go, oh, that's magic. It's 8 meters per second and I travel at 8 meters, okay? You'll see this only happens at 2-second intervals, at the end of the second interval, where your velocity and your displacement are the same number. That only works at that point. Don't look at that and go, oh, that's always going to happen. No, it's not, okay? It happened to work out that way. So at the end, I'm going to be at 8 meters, okay? And then at 3, I'm going to have 3 seconds squared times 2. We'll just shortcut that. 9, 18. It's a horrible 18. And then at 4, I'm going to have 4 squared. That's going to be 32. So basically, this graph is going to be so very parabolic. It's going to go something like this. Okay. Now, here's where we go full circle. Okay. Here's where we go full circle. I'm going to come in here at 1 second, and I'm going to draw a tangent line on this position time graph that's going to touch that curve at 1 second and 2 meters. Here's the question. What's my instantaneous velocity at the end of 1 second?
4 meters per second.
4 meters per second. So the slope of that tangent line is going to be 4 meters per second, because that's how fast it's going at the end of
1 second.
1 second. Now, if I come out of there to 2 seconds, what's the slope of that tangent line going to be?
8 meters.
8 meters per second. What do you notice about your tangent lines?
Getting
They're
steeper.
getting steeper. Why?
Because it's
It's acceleration.
Quadra-
Because you're accelerating because it's a quadratic function. Okay? So this is where it all goes full circle. This becomes a quadratic function because it's at squared. My velocity time graph is a linear function because it's acceleration times time. Okay? Quadratic, linear. The slope of these position time graphs gives me my velocity. That corresponds with this. Now, if we haven't talked about this yet, but what if I ask you to draw an acceleration time graph? What would an acceleration time graph look like? Yeah, that would just be a horizontal line at 4 meters per second squared. So if y'all are into calculus and being nerds, okay, this is where you take derivatives and integrals, okay, and that's where you go from a constant to a linear function to a quadratic function. And that's how the three all fit together, okay? Once you do calculus, you'll see, oh, yeah, that's where calculus works. Oh. Okay, got that. So here's my last and final equation. Now, as it is written on your sheet, you've got Vx squared equals Vx naught squared plus 2ax times x minus x naught. Okay? That's the big formal way to write it. Here's how this is functionally used. We just write v squared equals v naught squared plus 2ad. Or you could put x, whatever you want to do. Okay? So this is the functional version of this thing. Okay? It's rare that you take that, like that final position minus the initial position here. Exceptionally rare that you have to worry about that. That would only be if you like drop something off of, like you throw something up off of a building and then it falls all the way down to the ground. 99% of the time, just let that be the distance, okay? Now, this is the only one that has a name. This is what's known as that equation, okay? And that started many, many years ago, a kid by the name of Nettie. And he goes, Mr. Burkamp, can we just call it that equation? I said, fine, Nettie, fine, we'll call it that equation. And it's just stuck. And it only applies in this class. If you go to KU and you're in a lecture hall and you go, excuse me, can we use that equation? They're going to be like, no, go away. So it only works within the confines of this class. But that's that equation. Now, let's do a little bit of compare and contrast. So we have v equals v naught plus at. We have distance equaling 1/2 at squared plus v naught time. We have distance equals 1/2 v plus v naught time. Then we have v squared equals v naught squared plus 2ad. What's missing in that equation that's in every other equation?
Time.
Time. So if you ever get a problem that does not involve time, use that equation. Okay? That's it. That's your go-to, because that's the only one that doesn't involve time. Okay? So when you say, oh, there's no time, use that equation. That's what it's there for. Now, later on, when we study potential and kinetic energy, you'll see where that equation comes from. Okay? For now, just accept it. It's a great gift. Just go with it. Okay? Later on, we'll prove the existence of it. Okay? So here's how you would use a situation like this. So let's say that you've got yonder carrot car, and let's say it's moving at 10 meters per second, and you want this to speed up to 20 meters per second, and you do that over a distance of, 5 meters. Okay? So imagine this. You're driving your car, and you look down at your speedometer, and you're at 10 meters per second, because you got the nerd package on the car. Okay? The nerd package on the car, it's not miles per hour, it's meters per second. Okay? Your speed up to 20 meters per second. Are my velocity vectors getting bigger or smaller? Bigger. I got a distance of 5 meters, which is about now from here to that wall. Okay? I want to find my acceleration. So, if you look at this, and if you like the VDAT thing, V naught DAT, and again, you don't have to do that, but some people like that method because it forces them to say, okay, what variables do I have and what am I searching for? So here's the beauty of this test coming up on Friday. There's only 4 equations, and there's only 3 of them are here. You have to know the other one. These are the only potential variables that I can give you. There's no mass involved. There's no energy involved. There's no circular motion involved. Literally, this is a 4-equation test. You just have to know how to use it. That's it. And those are only your 5 potential variables. V naught, DAT. That's it. Nothing else. You don't have to worry about mass. You don't have to worry about coefficient of friction. Nothing. That's it. That's all you have to worry about. So, my final velocity is going to be 20 meters per second. My initial is going to be
10 meters per second.
my distance is
5 meters.
5 meters. My acceleration, it's a big question mark. I don't involve time. Now, here's what I don't want you to do. Okay? I don't want you to look at this and go, oh, I gotta find time. Seriously, kids get like, I have to find time. I will take 10 meters per second, and I will take 10 meters per second, and you laugh, but I've seen this done. So I'm going to take 5 meters and take 10 meters per second and divide that. My meters cancel out, my seconds flip up. Oh, I get a half a second. Now I have time. Can you do that?
No.
1,000 times no. Why?
Because it's not constant.
It's not constant velocity. If you don't have time in that equation, don't take distance and divide it by velocity to get time. Oh, scream, yell, write bad things on your paper, okay? That grow gray hair, okay? Bad things, right? If you don't have time, this is why we have that equation, okay? So don't flip out and go, oh, there's no time. Use that equation. Okay, now, so I'm going to go v squared equals v naught squared plus 2ad. So one of the things you've got to be able to do is solve this equation. Again, if you look at my sequence, I'm always gonna solve the equation first. And then I'm gonna put in numbers, okay? So, how am I gonna get A by itself?
Subtract v naught over
V squared minus V naught squared divided by,
2d.
gonna equal my acceleration, right? So I got 20 meters per second squared minus 10 meters per second squared divided by 2 times. Now, before you do any math at all, is my acceleration going to be a positive or negative value?
Positive.
Why?
Because it's speeding up.
I'm speeding up with
Positive.
positive velocity. Okay? I'm going to be speeding up with the positive velocity. On a velocity time graph, I'm going from this point up to that point. Okay? So don't do this. Don't take 20 minus 10 and then square it. No, oh, I've seen this done. Okay, I've seen this done. And it isn't like negative 10 squared either. Okay? It's 20 squared minus 10 squared. Okay? And then divide by 10. So what do you get?
200 divided by 20?
400.
10?
It's
400
30.
minus 100 is 300. So it's
100 divided by 10 is 30
It's 30.
meters
It's
per
30.
second
It's
squared.
30.
Yeah,
30?
this,
30.
Yeah.
yeah.
We're confident.
Yes.
I
Yeah.
know.
Okay.
Whoa.
What?
I
How
know.
do you get meters per second squared?
Well, up top I've got meters squared over second squared, right?
Oh, okay. So you
Down on the bottom I've got,
need out.
meters gonna cancel out, I get
Meters per second.
meters per second squared. Okay?
We.
Got it?
Yeah.
Cool? Okay, so stop that for a second. Okay, so the white piece of paper that I gave you is how I want my assignments done. Fundamentally, this sounds arrogant, but it's true. Your job is to keep me happy. Okay? The happier I am, the better your grade's gonna be. Okay? So, imagine I'm your boss, you're my employee, and I'll tell you, this is the format that I want this done. So, if you look up here, these first 6 questions are multiple choice. So here's what I want you to imagine. Here's your piece of paper. Come in here and draw a line down, maybe over like 2 or 3 centimeters, inch and a half, something like that. So what's going to go over here, and this is a sample that I've given you on that piece of paper so you see exactly how I want this done. The only thing that's going to go here is answers. The only thing that's going to go over here is the work that generates these answers. I do not want you to do the work over here and then box some number that I'm magically going to have to go search for, okay? These eyes have seen a lot in almost 56 years. I am not going to go through over here and search through and try and figure out what your answer is. Now, the first ones are simple, okay? 1 through 6, those are all multiple choice. So you can just go 1, 2, 3, 4, 5, 6, okay? Boom, there's your answers.
Wait.
There's no real calculations that you have to do on 1 through 6.
Is this
okay?
supposed to be on a separate piece of paper?
Oh yeah, these are on a completely separate sheet of paper. You treat this as like a page out of a textbook. Nothing is answered here. You treat this as like a textbook page. Okay? Now you can write on it, but I'm not going to grade anything that's on here. Like nothing. If I want you to answer stuff on a sheet like this, I will give you spaces to put your answers. Okay? You can write on it. But I'm not going to grade it. Okay?
Okay.
Now, when you get to question number 7, I say, can an object move with uniform acceleration and constant velocity at the same time? So when you go to answer question number 7, that's an explanation. That you can carry over onto the main part of the paper. Okay? You don't have to cram that all and like go down here. Okay? You can write that across. Okay? Now, when you get to question number 8, so I'm going to show you exactly how I want number 8 work. We're going to work number 8 together. Okay? So, on number 8, Corvette starts at rest, undergoes uniform acceleration for 4 seconds. It's the displacement of 50.4. What's the value of the acceleration? So, if what I would do, and you don't have to do this, but this is what I would do. I'd go V naught, dat. Okay? So at least I know what I have. So a Corvette starts at rest. What does that mean?
0 meters per second.
0 meters per second.
As my
Velocity.
velocity. So V naught is going to be 0 meters per second. What else do I tell you?
The distance,
Distance is going to be
50.4.
50.4, about half the length of a football field. Okay? What else do you got?
Time,
I got a time of
4 seconds.
4 seconds. What am I after?
Acceleration.
Acceleration.
Acceleration. Do I mention anything about final velocity?
No.
No. Now, could I use that equation?
No,
Why not?
because you don't have final velocity.
I have too many unknown variables. Okay? But what I have to find is an equation that relates displacement, acceleration, time, where I can find that value.
The second one,
The second one,
yes.
where you have
that other equation. I don't know.
distance equals V naught T plus
Yeah, the parabolic one.
1/2 AT squared,
Yeah.
right? Cool with that. This is what I would write down. Hey, I'm going to convey to Mr. Burkamp, here's the equation that I have chosen.
Cool.
What's my initial velocity?
0.
0. So V naught,
Oh, we got it.
that's gone. Now, what I would prefer that you do, because you're running with the big dogs now, is you solve this equation for your unknown. What's your unknown?
Acceleration.
So you're going to multiply by,
2.
divide by,
Times.
and that's going to give me my acceleration. Now I'll put in the numbers. So now I'll go 2 times 50.4 meters divided by 4 seconds squared. Now, you don't have to show me 2 times 50.4 is 100.8 and then divide that by 16. That's why you all have calculators, okay? You don't need to show me the sub-calculations out of this. I know 4 squared is 16. Okay, I know 2 times 50.4 is 100.8. I don't need to know that, okay? Once you get here, then you can just get your answer. So what do you get out of all that whole thing?
6.3 meters per second.
What'd you get?
6.3 meters per second.
Exactly?
Yeah.
Now, every measurement I've given you has 3 significant digits, which means all these answers should have 3 significant digits. So that should be 6.30. So what I want up here is 6.30 meters per second squared. Okay? Now, when you get to number 9, here's what you do not do. Do not put the answer to number 9 here and then have the work for number 9 down here. I will absolutely flip out. Okay? You want to keep that answer right beside number 9. You want to imagine these being stacked. You want to view this from my perspective. I'm going to have, like, for your class, 11, or if I have in my other class, I've got like 26 kids. I'm not going to have time, love y'all to death, I'm not going to have time to sort through random numbers. Keep me happy. I prefer that you actually leave a space in between these, because that way I can go, oh, here's where number 8 stops, here's where number 9 begins, okay? Ideally, there would be a visual break in there. Some kids really get into this. They'll do like double lines and they'll put like stars or they'll shade it, okay? You don't have to go to that extreme. But I have had kids do that. It's like, you have way too much free time. I appreciate it because it's easy for me to see. So then you're going to have number 9, here's that answer. A lot of these are going to have multiple parts. So for example, on number 9 on the back side, You're gonna have motion diagrams. You're gonna have a velocity time graph. You're gonna have calculations. Keep these separate. Do not blend them together, okay? Again, don't view it through your eyes. View it through my eyes, okay? Louis.
Those graphs, do you want them on here or actually on graph paper?
So on, like for example, on number 9, when you're going to draw that velocity time graph, if you want to draw it on another sheet of paper, you can. These are just going to be sketches, so you can just do a sketch and put it on this paper. But if you're going to put it on this paper, draw it big enough so that I can see what is labeled and see what the numbers are. Now, pay attention on number 9. I say make a velocity time graph. I want the initial velocity, the time when she is stopped, and the slope of the line. So there's a whole bunch of things that you need to put on that particular velocity time graph. Okay? So, when you get to question number 15, okay, so let me make sure everybody's cool on number 15. So on 15, you got a driver driving at 20.0 kilometers per hour, stops the car in 3 meters. Later, while moving at 40 kilometers per hour, stops the car at the same acceleration. Draw the motion diagrams. What's the value of the acceleration? So you have to work off the MKS system. You cannot leave that in kilometers per hour. So remember, so on number 15, first off, what value is missing from number 15? What variable is not there?
Time.
Time. On 15, you're going to use that equation. Okay? That's a classic example. You're going to use that equation. Now, here's the deal. You got to take 20.0 kilometers per hour, and you got to change that into meters per second. Here's the short version. 1 kilometer, 1,000 meters, 1 hour is
300.
the zeros cancel out. The short version is you multiply by 10 and you divide by 36. Okay? When you do this conversion, this has 3 significant digits in it. When you do that conversion in meters per second, you want to keep at least 3 values. Okay? Do not round those sub-calculations. So, right quick, just got a calculator. Take basically 200 and divide it by 36. I think it's 5 point something.
5 point a lot of fives.
5 point? 5555?
Yeah.
Okay? So I think if you can get by with 5.56, okay? But certainly don't do this. Do not look at this and go, oh, I'll just call that 6. Bad, horrible, stop, no, okay? So when you're doing those sub-calculations, keep at least the same number of digits as the value that you have. So at least keep it as 5.56. Now, you have some stuff from your book. At the end of every chapter, there's 2 distinct sections. There is the question sections, and then there's the problem sections. Okay, so if you look at the end of at the end of each chapter, easy for me to say, there's a problem section, there's a question section. That's what this is referring to. Okay, and again, I want the same format on anything that you answer. I want answers on the left. I want the work on the right. Okay, you can write on this whatever you want to do, but I will not grade anything that is on here. Okay. You can circle your multiple choice answers. I don't care. I'm not going to grade it. I'm only going to grade what's written on that sheet of paper. Okay? All right. I can preach to you all day about these equations. Until you begin to actually do them, work them on your own, that's how it's going to play out. So today's Tuesday. We're done with all the equations. There's no new equations to learn. Okay? We've got them all. Tomorrow we're going to apply these to gravity. Thursday we'll review, test on Friday. So that's the drill. Okay, Vitor,